Hello and welcome to ECMath. Today we're going to talk about polar points and the polar coordinate system. So the coordinate system you're probably used to, we call the rectangular coordinate system. It's based on a grid, x, y axes. It's also called the Cartesian coordinate system, and it's good for graphing, well, rectangles. But a lot of things in the world are not rectangles, and it turns out that to graph things like circles and other curvy-like objects, it's actually better to have a coordinate system called polar. And just to put a rectangular grid and a polar grid together for a minute, you'll notice that they still have sort of a center. There's a lot of things in common, but instead of x and y, you have these lines radiating out from the center, and that's what creates the polar graph. Usually, you can download sheets of polar graph paper, and they come in a little sheet with 6 or 8 to a sheet just like this. I will post one to our class and share with you, but you can also just search for polar graph paper to find them. It might be good to print out a sheet like that as you watch this video to take your notes, just to make your life a little easier. So we're going to start by labeling the parts of the polar graph. And the first part we should label is the pole. The pole is the center right here. That's what we call the pole. In rectangular, that's called the origin. In polar, it's called the pole. We're also going to label the polar axis, which is basically the equivalent of the positive x-axis, but it only goes off to the right. And that's the axis where we start graphing. So we're going to graph from the polar axis around the pole in this direction, instead of going over and up. And then we can look at this graph paper, and let's just explore it for a second. We're going to be in radians as we do this. Now, you could do polar in degrees, and some people do, but for us, we're going to be radians all the way here. And the angles work the same way that they've always done. They open in standard position from the polar axis all the way around, and then when you get to the terminal side of the angle, maybe over here, you label the angle, and I'm going to label it around the outside. So this angle we just labeled in radians is pi. I guess the polar axis is 0 radians and degrees, or 2 pi. We have pi over 2. We have 3 pi over 2. Everything's familiar here. Now let's label some of these ones in the middle. The ones directly in the middle that divided into eighths, those are the pi over 4s. And what I notice about these other lines is there's actually 24 of them around the whole circle, or 12 in a half circle, which means that each of these lines is actually a pi over 12, which is not an angle we've dealt with before. But the reason they do it this way is that if you do pi over 12 as your smallest angle, you get all of the pi over 4s, 3s, and 6s, because they're all divisors of 12. So that's pi over 12, but let's go label the important angles, the ones we actually care about. There's pi over 6. Then this would have to be 5 pi over 6, 7 pi over 6. Here's 11 pi over 6. And we also get the pi over 3s. Two. And then these ones we didn't talk about are all the different pi over 12s, which you can label in. There they all are labeled in, but you don't really need to know the pi over 12s. Just understand what the denominator is. So this is like a polar plane with all the angles labeled all around. You can get polar graph paper that divides the angles even smaller or even larger. This is kind of the standard, but you can get it in different sizes too. There's some apps online that generate different sizes of polar graph paper. So depending on how fine of a resolution of graph you want to do, you can change your scale around based on the paper you generate, just like you can with rectangular graph paper, deciding how big your squares are. All right, so going to a clean polar graph, here's how you plot points in the polar system. Every point is always of the form r, theta, and it's always in that order. And that can be confusing because of the way the angles come and the way the radii come. So just you have to remember that they're always of the form r comma theta. And the way you're going to graph a polar point, and, maybe there's other people that do it differently, but the way I like to do it is I actually look at the angle first, and I rotate to the angle, and then I look at the radius and I count forwards from the pole, which was the center. So let's do 4 comma 2 pi over 3. I'm first going to find 2 pi over 3. So I'm remembering what I labeled before. This is the pi over 12. So here's my 2 pi over 3 angle. The point for 2 pi over 3 lies somewhere on this ray. And I go to the pole, and every ring counts as 1, or at least in the default scaling. You can assume that every ring counts as 1, unless it's marked differently. So you just count out 1, 2, I'll mark it, 3, 4. And at that point where you're at the correct angle and the correct radius, you can plot the point. It might help to put the polar axis in. That's where you're always going to start counting your angles, is from that polar axis, positive x-axis, just like in rectangular angle situations. You might want to try B and C on your own before I do it. So, take a pause and check it out on your own if you want to. All right, so let's do 2 comma negative 5 pi over 6. So I'm going to do the angle first. I'm going to count around to negative 5 pi over 6, which is opening this way. And it has to be here. So my angle will be, or my point will be somewhere along this ray, going out from the pole. And I'm going to count out from the origin, 1, 2. So then the point is right here, and we'll label it. I'm sorry, it's a little hard to read, but maybe that helps. That's the point for B. So negative angles work the same as they do in like normal trig applications. You just go clockwise instead of counterclockwise. Now let's plot point C, which is negative 4 comma 5 pi over 3. So there's a little negative here that's going to mess with us. But let's first find the angle. So we're going to check the angle first. 5 pi over 3 is all the way around down to here. 5 pi over 3, just my normal unit circle. So the point I want is going to live somewhere along this ray. Now, if I were to count out along this ray, I would count 1, 2, 3, 4. But I'm trying to find negative 4. So instead of counting in the direction of the angle, what you're going to do is count backwards. 1, 2, 3, 4. And actually, this is on purpose, we land on the point that we already hit. So this was point A, but it is also point C with representation negative 4 comma 5 pi over 3. And that's how you deal with negative angles. And you won't always land on a point you've already plotted. Did I say negative angles? I meant negative radii. You won't always land on a point you've already plotted, but you just find the angle and then you go backwards, which makes sense, right? Like that's how you deal with negative x coordinates. You go backwards from the direction you would normally go. So that's how you deal with negative points. But the notion that A and C are the same point actually leads us to our next thing. Polar points are not unique in their representations. Unique would mean there's only one way to write it, and rectangular points are unique. 1, 1, there's no other way to write 1, 1 in the rectangular coordinate system. We can switch coordinate systems and write it in some other way, but would have to write it as 1, 1 in rectangular. In polar, though, because we're going on a circle, and we can either have positive or negative angles that get us to the same place, right? Positive angle, negative angle could arrive us at the same place. And we can have positive radii or negative radii. We actually have a lot of different ways to get to the same point. That's one of the cool things about the polar system. So here's the point B that we plotted above. In the previous example, it's at the coordinates 2 comma negative 5 pi over 6, which I've shown here. Now, there's two ways that you can find an alternative representation. The first is to use our standard idea of coterminal angles. So we rotated to negative 5 pi over 6 when we constructed that point. But there's no reason that we couldn't have started at a positive rotation, started at 0 and done a positive rotation instead, and just notice that this is also 7 pi over 6. And algebraically, the way we can do it is just negative 5 pi over 6 plus 2 pi, that is one full circle, takes us to exactly the same place we started. So you can always add 2 pi to the angle and get another representation of that point. That's what I've represented in this first statement here, that r theta is equivalent to r comma theta plus or minus 2 pi. You can add or subtract 2 pi to get the same point with a different angle representation just because it's added or subtracted a trip around the circle. But when we're plotting points, we don't care about the number of trips, we just care about the end result. The next one's a little bit sneakier. Because we're allowed to have negative radii, if I'm still trying to get to this point, what I could have done is gone to this angle and counted backwards 1, 2. So like at a radius of negative 2 with respect to the angle over here. So I'm going to think about what angle that would be. I guess it's in the first quadrant with a size of pi over 6, so it's just pi over 6. So another representation of that point would be negative 2, comma, just 1 pi over 6 in the first quadrant. So there's two representations of that point, either by going a full circle around or just 1/2 circle around and changing the radius to negative. This idea of going a half circle around and changing the radius to negative is what I meant here when I wrote negative r comma theta plus pi. So here you change your radius from positive to negative, or negative to positive, I guess, if you're already have a negative, and you go a half circle. So I don't really like to use these as equations. I usually just sketch out the points and do it geometrically, but everyone can kind of do their own thing here. So that's how you write equivalent representations of polar points. All right, finally, I'd like to talk about how to convert points from polar to rectangular or rectangular to polar. And there's a series of conversion factors that we can use. They're actually pretty familiar if you have been thinking hard as you do the trig section. And here they are. So I have here a polar grid, but I've also imposed on it in orange a coordinate XY axis. So we have the standard pole and angle, but we also have XY. So the XY, if we had like a graph paper under here, would look like this. We'd have Y and X. But if we were in polar, we would instead have an R and an angle theta. And this would have the same coordinates R theta as it would X and Y. And we need a way to relate R theta to X and Y. And I know that this specifically probably has coordinates, what would it be? 6 and pi over 3. But I'm not going to worry about the specific coordinates. We're being general here. So just think about this as a generalized point. Well, the first thing I notice is that this is a right triangle. So the first conversion factor is that x squared plus y squared must always equal r squared. Hey, that's really familiar because it's basically the equation for a circle. The second conversion factor is maybe relates to the angle, which is that if I think about trig in the triangle, it would be true that tangent of theta would equal y over x. That's actually, maybe I should have written that one last. That's the least important or useful conversion factor, but it's a true conversion factor. Then, if I kind of think about x and y instead of the theta, I could also write the conversion factors. Well, let's think about this theta for a second. So theta is across from y with a hypotenuse of r. So a little scratch work, it would be true that sine of theta is y over r. Hey, that's really familiar to us. Now, for some reason, we don't like fractions, and it's actually weird to have y and r on the same side since they're from different systems. So what we'll do is multiply this by r and get the conversion factor. Where is it? There we go. Y is equal to r times sine of theta. And similarly, since cosine theta is x over r, little scratch work, multiply by r, you get x is equal to r times cosine theta. These are our 4 conversion factors using rectangular to polar, polar to rectangular. Put a big box around that and say, know these. You must know these conversion factors to be successful with converting polar equations. That is one of the things that comes up the most often when I use polar later on, is these conversion factors, because they can help us convert not just points, but also entire functions using these factors. So make sure we know them. But today we're just converting points. So let's do 2 quick examples. So we're going to convert polar to rectangular first. So I have the 4 comma negative pi over 3. So that's the r and theta. I'm going to go ahead and plot that point on the system just to see what it looks like. Now, what I actually usually like to do here in the case of converting a point is just draw a triangle. We know the angle, we know the radius, and we could just do some trig work here. But the conversion factors actually have already got that built in. We kind of made the factors based on everything, all of our triangles already. So we don't need to necessarily go back to the triangle. Instead, I can just use the factor x is equal to r cosine theta. So that would be 4 cosine of negative pi over 3. And y would be 4 sine negative pi over 3. Now, I kind of think back to my unit circle, and I remember that cosine of negative pi over 3 is positive 1/2, and sine of negative pi over 3 is negative, because it's in the 4th quadrant, negative root 3 over 2. So that would be 2, and that would be negative 2 root 3. So the coordinates of this point in rectangular would be 2 and negative 2 root 3. And you could still get that by drawing a triangle, but those would be effectively the side lengths of, make it bigger, effectively the side lengths of the triangle that you would draw anyway. So that's converting polar points to rectangular points. Now let's try converting a rectangular point to a polar point. All right, so we're converting rectangular to polar, just made it a little larger. So we're doing 3 and negative 3. Now we can use the conversion factors here, but I still think it's a little easier to just sketch a picture. So since I have a polar grid up there, I'm going to draw a rectangular grid down here and then see if we can figure out the r and theta. So I'm at 3 x and negative 3 on the y. So that's got to be down here. And I would be looking for the r and the theta of that point. Now, let's use the conversion factors we know. So to find r, we can use the factor x squared plus y squared equals r squared. And so we'd have 3 squared plus negative 3 squared equals r squared. That ends up being 18. So the square root of 18 is r, and that ends up being 3 root 2 equals r. A faster way to do that, if you didn't, if you recognize this point, is just to recognize that this is actually an isosceles right triangle. So it has the relationships x, x, and x root 2. And, we have 3, negative 3. So it would have to be 3 root 2 there. You can usually use your special triangles, but not always, right? You might not have a point that lies nicely on the line. So then you really do have to use x squared plus y squared equals r squared. And that will always work for polar points. Now, finding theta. We could probably recognize what theta is at this point because we said it's an isosceles right triangle, but it won't always be that way. So let's check it out. We have the conversion factor that tangent of theta is equal to y over x. So we have the equation tangent of theta is negative 3 over 3 or negative 1. Now, we could solve this with inverse tangent, right? And do tangent inverse of negative 1 equals theta. That will work, but remember, I'm going to put a star next to this. Remember that inverse tangent only outputs in quadrants 1 and 4 on your calculator. And if you've drawn a sketch of the point and you're actually over in quadrant 2 or 3, you might need to add pi to your angle to get like a good answer that you actually matches with the point. So you don't just blindly use inverse tangent. I would really recommend making a sketch because the value of that answer will depend on the quadrant that you're in. Now, in this case, I'm actually in quadrant 4 already, so I could do inverse tangent of -1. Just double checking that I'm in radians, which I am. And we can do tangent inverse -1. And we get this decimal. Now, again, your calculator, it's not smart. It only knows decimals. So let's double check. This angle just feels like it has to be -pi/4. And the way you can see if your calculator is being smart is, yes, that actually is -pi/4. You just type it in and see if it matches. So in this case, theta equals -pi/4. Or remembering our alternate representations of points, maybe you wanted a positive angle. You're like, negative angles are for losers. Then you could write that theta is also equal to 7pi/4. So this point in polar has a radius of 3√2 and an angle of -pi/4, or 3√2 and 7pi/4. And at least in this application, I don't really care which, either is fine. Just make sure you're doing your angles correctly. And really, other than that goofiness with inverse tangent, that's how you have, it's pretty easy to convert points between polar rectangular and rectangular to polar. So here we go. That's all we have for you today, folks. Stay tuned for the next video where we're going to talk about what are the applications? Why do we care about the polar system once we kind of know these basics about plotting points? So stay tuned for that one, and I'll see you all next time.